Can you hear me? So, okay, let's get us started. Is it too loud? I guess so. Is it better? So, good afternoon. Welcome back to another lecture in digital design and computer architecture. Today, we're going to continue what we have started in timing and verification. I've been waiting actually for this lecture because this is actually one of the most exciting topics in digital design. And I really hope that you guys also enjoy it. As a reminder, these are some readings that we have for this week. And next week, we're going to start von Neumann processor microarchitecture foundation that we need for that. So make sure that you also check these readings for next week. And basically, we were discussing about circuit timing yesterday at the very, very end. And we say that basically we already know how kind of investigate logical functionality, but we wanted to know about timings and how fast is the circuit, how can we make a circuit faster, and what happens if we run a circuit too fast. And basically, we mentioned that a design that is logically correct can still fail because of real-world implementation issues. And we basically reached to this point that we wanted to start about combinational circuit timing. So the digital logic abstraction that we are using is quite convenient. That, for example, we assume that we can output changes immediately with the input. So here is a NOT gate, and A is the input, and immediately after, basically, first immediately A can go to 0, so this is sharp, and the output of this gate also immediately goes from 0 to 1. So this is a convenient abstraction that we usually consider when we want to talk only about the functionality of the circuits. But in reality, that's not the case. So outputs are delayed from inputs because transistors take finite amount of time to switch. So for example, here we have a buffer gate. This is, be careful, this is not a NOT gate. So the input A actually goes from 0 to 1. This is also not that ideal, so it's not sharp. And the output takes some time to react, essentially. So this is the delay that we have. Even actually this diagram is also a kind of abstraction because what we have seen in real world is actually something like that. You know, we don't really have lines in these kind of waveforms. And you can actually define different kind of timing. So we're going to see the definition of them, but this is one of the timings, for example, the amount of the latency that you need to wait for the output to start changing. So this is the latency for that. And here is also another latency that is kind of propagation latency, the latency that you need to wait until your output is stable, essentially. But we're going to learn about these definitions. So delay is fundamentally caused by capacitance and resistance in a circuit. Whenever you design a circuit, like every gate that you have has transistors. And first of all, when transistors gets on, they don't act as a basically single wire. So they can act as resistors. And also all of them, they have a capacitor. So you have also parasitic capacitance in all wires, in transistors. And all when you want to change the output, essentially, very likely you need to go through this RC delay. So you need to charge a kind of a capacitor. And from your study, I guess, in physics and maybe from your high school also, you know that would take some time. So you cannot immediately charge the capacitors. Similarly, when you want to decharge a capacitor, that would take some time. So that's one of the reasons. Another one would be also the finite speed of light. So we know that the speed of light is fast, but not so fast on a nanosecond scale. So anything affecting these quantities can change delay. Rising, meaning that going from 0 to 1 and versus falling input. So each of them can also cause basically and cause delay in your circuit. Different inputs have different delays. If I want to also give you some insight is that think about the NAND logic that we discussed. The NAND circuitry in CMOS. So we had two NMOS transistor in series, and we had two PMOS transistor in parallel, right, in the pull-up network. So from that, you can see that actually in pull-up network, you have two transistors that they are in parallel. So from Kirchhoff's law, you know that you have better current to charge a transistor. But in the pull-down network, you have two transistors that they are seried. So that can actually reduce your current. So that's very simple example that shows you basically different input. So for example, going from 0 to 1, in the output can take less time compared to going to 1 to 0, or the vice versa. And any different input vectors can also have different latencies. Also, changing the environment, like the temperature, or for example, the voltage, supply voltage that you provide to the circuit, that can also affect the latency, as well as aging of the circuit. So as you use your circuit more and more, your circuit is going to age. And with that, actually, your latency can increase. So we have a range of possible delays from input to output that basically designers need to deal with them. So we have in order to find a good kind of simple abstraction, we're going to define these two delays: contamination delay and propagation delay. Contamination delay is delay with until output, which is y, starts changing, and propagation delay is the delay until output finishes changing. So we can see from this example, this is a circuit, and AB are the inputs, and Y is the output. So the moment that we start changing the one of the inputs, which is A, you can see from this circuit that this is the amount of time, minimum amount of time that you need to wait until your output starts changing. So we call this contamination delay, essentially. So this is the amount for contamination delay. And from starting the changing of the input, and also until the output finishes changing, we call this propagation delay. So this is the definition of propagation delay, and that the first one is the contamination delay. We usually need to, when you want to make sure that your circuit is stable, you need to basically make sure about, basically you need to calculate propagation delays. But when you want to also make sure that any single change is not affecting the result of your circuit, you really need to also be conservative, and you need to check contamination delay. We're going to actually see a lot about this in this lecture, so don't worry if you don't understand it clearly now. And this is the notation that we usually use in waveforms. This cross-hatching means value is changing. So it's just a kind of notation for waveforms, essentially. Okay, so we need to calculate longest and shortest delay paths. We care about both the longest and shortest delay paths in a circuit. And we will see actually the reason in this lecture later. Here is an example. You have this one AND here, and then the output goes to this OR, and then you have AND. So you can, by checking this circuit, you can see that probably the critical path is going from A to the Y, essentially, right? So you need to go through this AND, and then through this OR operation, and then through this AND operation. So this is the critical path, or the longest delay path of your circuit. And very likely your shortest path is going to be this, from D to Y, right? Because it only goes directly to this gate. So if you want to calculate, for example, the minimum latency of this circuit, you need to basically check the shortest path. If you want to calculate the critical path or longest latency of this circuit, you need to go through the critical path latency. So essentially, critical longest path, for that we calculate basically the latency of propagation delay is going to be basically one propagation delay of this AND, and then one propagation delay of this OR, and then one propagation delay of this AND. So in the end, we're going to have two propagation delay of AND plus one OR, right? And for the shortest path latency, we need to calculate based on the contamination delay, as we already discussed. So we only consider the shortest path of the circuit, and we only calculate the contamination delay. So the contamination delay of this whole circuit is going to be the contamination delay of this AND, essentially, only, right? Does it make sense? Okay. So let's see with some examples. Here we can see, for example, this is the circuit, and these are the initial inputs that you had, like A1, B1, C0, and D1. So with that, if you calculate, you can see that the output of Y would be 1. Then you change the input A to 0. So this is your transition from 1 to 0. And things needs to get propagated, essentially. So this is actually a very good example because you need to go through all these gates. So this AND gate, in the past, it was 1. But now, because A is 0, so you need to wait for that until N1 gets to 0. And then when N1 gets to 0, then this OR also needs to get 0. So you need to also wait for that, such that N2 also get from 1 to 0. And after having 0 in N2, then you can actually also see that Y goes from 1 to 0. So it's actually exactly propagation delay. So your delay is propagating as you go through this critical path of your circuit. And for the shortest path, considering this basically initial vectors, A, 1, 1, 0, and 1, and then for D, you go from 1 to 0. So you know that the output should go from 1 to 0. But this will happen very, very quickly. So this is the propagation delay. But you can, until here is the propagation delay, but you can calculate the contamination delay that D when it starts changing and until Y also starts changing. So because of that, we calculate the contamination delay of the AND gate for the shortest path. Does it make sense? Any question? Good. Okay, so now I'm going to provide some examples about propagation delays for some different gates. So here is an example of a real NAND 2 gate. Actually, it's from this IC. They are actually very famous, 74XX. And they are from Texas Instruments, as far as I remember. In the past, they had the TTL, which is actually completely different technology to make your circuit. It's using BJT transistors, which they are different from NMOS. But after that, they also started using CMOS. So in this IC, you can see that you have 4 NAND gates, and you can use each of them separately, essentially. So what I want to show you here is that essentially, depending on the voltage, the supply voltage that you apply to your IC, you're going to have different latencies. So as you increase your supply voltage, your latency decreases. And depending on the temperature that you're working on, you have different latencies. So essentially, you can see that by working on the lowest temperature and also the maximum voltage, your latency would be 7 nanoseconds. But it can be up to 135 nanoseconds if you work with 2 volts and also the temperature of 125. So that shows you that basically propagation delay heavily depends on voltage and temperature. It also depends on the way that you implement your circuit. So here is an example of 2 different ways of implementing a multiplexer 4-to-1. This is the way that you calculate the min terms and then you do OR. And this is another way that you use a tri-state buffer. And you can see that the propagation delay are different between these 2 designs. So depending on how you implement your circuit, you're going to have different also latencies. Here is also another way of implementing multiplexer using 2-to-1 multiplexers. But it also has different latencies. So basically, the goal for this slide wants to show that essentially these latencies of our circuit are heavily dependent on the voltage, temperature, the way that you design, and also the input vectors. So we didn't show that here, but essentially when you change for different input vectors, you're going to have different latencies. And all our tools that they need to deal with all these latency calculation, they actually need to consider different input vectors for accurate estimation. But here I want to provide this disclaimer that essentially it's not always this easy to determine the long and short path. So you observe that in that circuit, it was so easy to see what is longest and what is shortest. Basically, not all input transitions affect the output. So this is very important to verify. And also, it can have multiple different passes from an input to output. So your output is derived through different passes. And you need to deal with all of them together to understand which one is the shortest, which one is the longest. So it's not really easy. And usually it's automated using CAD tools. In reality, also circuits are not all built equally. So different instances of the same gate have different delays. Here I showed you real ICs that with some delays. But in that series also, we have different version of that IC. Even for NAND gate, that they have different delays and access latency, different delays essentially. And wires also have non-zero delay. because essentially wires also can be modeled by capacitors and also resistors, and it can increase with the lengths. And temperature voltage also affects circuit speeds. And even with these, when you put all this together, you can actually see that sometimes it can even change the critical path of your design. So when you use a different circuit and with different temperature, also with different voltage, you might have a completely different critical path as you thought before. So in the end, designers assume worst case conditions and run many statistical simulations to balance yield and performance. This is a usual way of designing, but this consideration of worst case and designing for worst case scenarios actually cause a lot of inefficiencies in our today's systems. And you're going to see a little bit more later in our lectures that we don't need to be that strict and always design for worst case. So you can also design some intelligent techniques that can decide based on the situation, can work for the best case, or sometimes basically try to make the more intelligent decisions on the status that you have there. Yes.
So the clock cycle doesn't strictly depend on TPD.
It actually, we will reach that later soon. Yes.
How does a wire relate to, can we model it as a capacitor? Because I understand how it works as a resistor.
That's also a bit out of the scope of this course. We can discuss later offline, but essentially, if you look into electronics, usually when you're especially when you have long wires, when they want to model the way of the wire, they need to consider some capacitors and resistors. So there is a lot in electronics about that, but we can also discuss it offline. Any other question? Yes.
Why does aging of the circuit affect delay?
Why what? Sorry, say it. Oh, aging. Okay. So aging can affect the effectiveness of your transistors, essentially. That's one reason, for example. So your transistors, so normally, for example, you consider that your transistor, when it's on, it can drives that much, current. But after using it a lot, doing it on and off, it can cause some issues. So its performance of that transistor can reduce. There are also many other reasons for that, which is, again, out of scope, but we can also discuss offline if you're interested. Was that insightful? Okay, yeah, good. Any other questions? Good. So, yeah, this is a summary of what we have discussed already about these delays. Now let's also quickly take a look at glitches that we briefly talk about it. So glitch are actually one input transition causes multiple output transitions. So here is an example. Look at this circuit. We have this initial state, and basically we want to the initial state actually was 0, 1, 1, and the output is 1, essentially. And you want to move from 1 to 0. So this input wants to go from 1 to 0. So let's see what would happen. So the thing is that usually glitches happen when you have different paths to drive output, and you have slow and fast paths. So here you have this slow path that pass through 3 gates, and here is your fast path that pass through only 2 gates. So as a result, you can see that the output will go from 1 to 0 and then to 1 again. Why is that? Because when you move from 1 to 0 here, so this becomes 0, and the output of this AND would be 0. And because of this OR operation, that this initially was also 0. So this OR operation is going to make the output to 0. But after some time, you also get another value for this OR, which is 1. And then you need to go to 1, essentially. So that's the reason that you might see some glitches in your circuit. So glitches, yeah, here is basically the diagram that I already discussed, why it's happening like that. And the output, for a very short amount of time, it can go to 0 and then come to up to high voltage. Yes?
And that time is TPD minus TCD. Right at most.
Yeah, around that, yes. But it's not that easy to calculate like this. I mean, you can use this abstraction in your mind, but usually these delays are not. They are not calculated like these numbers, like these equations easily. So there are a lot of. Sorry. No, we don't navigate. What did you ask? Sorry.
So like, is it just the probability where it lands?
No, it's not probability. So it is like. So first of all, these delay, like contamination delay and propagation delay, they have very exact meaning. For example, propagation delay means like 50% of input to 50% of output, something like that, you know. So if you consider that, then you cannot easily say that, you know, propagation delay minus that. So these are not that accurate. But I like your abstraction, basically, you know, it's good for understanding. Any other question? Okay, so this is optional. I'm not going into it in detail. If you were interested enough and you checked Carnot map, that we had some lecture on it, not lecture, some slide. That was optional. You can. There is a way to avoid glitches by going through the Carnot map, but I'm not going to cover it because you can check it if you're interested later. This is optional, as you can see. But essentially, you can. What you can do is adding a circuit here. This additional AND gate. So you can see that now this circuit is not minimal. So you're adding another gate. But by adding this, you make sure that there is no glitch in your output. So now the question is that, do we always care about glitches? So first of all, fixing glitches is usually undesirable because it can consume more chip area, more power consumption, and more design effort. And the circuit is eventually guaranteed to converge to the right value regardless of glitchiness. So the answer is that no, not always. So if we only care about the long-term steady state output, we can safely ignore glitches. And it's up to the designer to decide if glitches matter in their application. So glitches also can affect some unnecessary dynamic power consumption as well, because your output is going down and then coming up. So that's some power consumption that you're consuming. But to avoid glitches, if you add circuits, you know that those circuits are going to also consume power. So it may not worth it. But you remember that, for example, when I was presenting about Mealy and Moore machine, I said that Moore machines are better in terms of avoiding glitches. The reason is that in Mealy machine, when you change the input, that input can also cause some glitch in your output. And that output might be also the input for some other Mealy machine. And that can also cause some glitches in some other, another Mealy machine, and this can propagate. So one simple glitch can actually propagate to many, many other circuits, which can consume a lot of power. So that's why we actually, when we design our sequential circuit, we usually prefer Moore machine, as long as they don't, you know, they don't need a lot of more states compared to Mealy. And they can work very well for glitches, for example. Okay. Now we can take a look at sequential circuit timing, which is a bit more interesting. This is a recall for you that D flip-flop, as you remember, that basically flip-flop samples data D at the active clock edge. So the important thing about D flip-flop is that data must be stable when sampled, meaning at active clock edge. So this is your clock cycle. So your clock cycle also is not ideal. So it cannot, you know, goes to one sharp. So it's going to be like diagonal. And then essentially your data, in order to be sampled reliably, should be stable from this amount of time before rising edge of this clock. So this amount that we call it setup time. And it should be also stable a bit after the rising edge, which we call it hold time. So if you don't follow, if you basically don't follow it, then you might get into some meta-stability situation of D flip-flop. And then essentially in the end, you don't know what is stored in that D flip-flop. So setup time, the definition is that time before the clock edge, that data must be stable, meaning that there should not be, basically the data is not changing. And hold time after the clock edge, that data must be stable. And there is also another terminology, aperture time, which is time around clock edge, that data must be stable, which is the summation of T setup and T hold. You had, no, okay, yeah.
Would we use an enabler for this?
Say it again, sorry.
Would we use an enabler for this, like an enable D flip-flop?
So for enable D flip-flop, that's yes. For enable signal, also you should make sure that you activate enable signal soon enough. But the thing is that you are not sampling enable basically signaled in your D flip-flop. It only talks about your data. Oh, the way that we implement, you're asking. Yeah. Okay, no, it's not about enable. We're gonna see how we ensure that soon, yeah. Yes?
What is the signal? Is that don't care or is that float?
This part? Yeah, like you're saying that, okay, the D is changing, because there is a circuit, there might be a combinational circuit that's driving D data here, right? So that circuit is causing some D to be like changing. There might be a lot of changing here, but I don't care. But what I care is that from this time, D should be stable. Yeah. Any other question? So this is what I talked about meta-stability. If D is changing when sampled, meta-stability can occur, and flip-flop output is stuck somewhere between 1 and 0. In the end, output eventually settles, but this is not non-deterministically. So you don't know if it's 1 or 0, essentially. And this is an example that for NAND RS latch, that this is the region for meta-stability that you don't, something between 1 and 0. And in the end, you converge to 1 or 0 in the end. But you don't know because this is non-deterministic. So you should avoid. Basically, designer should avoid violating setup time and hold time. So similar to combinational circuits, we also have some timing that we should define for flip-flops. So the moment that we have this rising edge of clock and the amount of time that takes time for the output to react. So we have two. One is that contamination delay clock to Q essentially, TCCQ, which is earliest time after the clock edge that Q starts to change, which is unstable. And we also have this propagation delay clock to Q, which is latest time after the clock edge that Q stops changing, meaning that Q is stable. So yeah, essentially from this figure, you can see this is propagation delay from clock to Q. And this is your contamination delay from clock to Q. And Q starts changing from this time. And it's basically stops changing and is stable exactly at this moment. Yes?
Yeah, one question. Where is Q in this meta-stable state? What's the reason for it?
Well, here, the thing, so because your circuit, as I said, like the way that we implement the flip-flop, right? It was, for example, 2 latches, first and second latch. And each latch, for example, is a D latch and has, for example, several NAND gates, right? It can be also different version of it, but overall, there are some gates. And all these gates needs to react, to have some, basically to have your output, right? So you, for example, your output wants to rise from 0 to 1. So it cannot get to 1 immediately, right? It will take some time. And when you sample during that time, for example, you can see that, okay, it's not, so your 1, logic 1 might be like 5 volts, for example, So if you sample, you're going to see that, okay, at this moment, my output is 1 volt, which is not 0, which is not 1 as well, logical 1. Then you need to wait a bit more. You're going to see, okay, my output is 3 volt, and then 4 volt, and then in the end, it's going to be 5 volt. So you always want to have this stable situation that your output is 0 volt, which is logic 0, or high volt, which is logic 1. And between that is your unstable situation that you want to avoid, essentially. Any other question? Yes.
For better understanding,
yeah.
Compensation delay, does this depend on what kind of gates that we use?
It doesn't. Yeah, it can also depend partially on the gates that you're using, but in the end, for contamination delay, it depends on your shortest path of your circuit. And also, when you want to calculate contamination delay, you need to actually consider best case scenarios for latencies, essentially, in the sense that you consider everything to be fast as possible. Because for contamination delay, we want to be as conservative as possible, because we want to say that the latency, the latency of this circuit is not going to be lower than this amount, for sure. So for that, we are very conservative. Because if we don't, you're going to see why that is very important. But you should know that the latency of this circuit cannot come lower than that. So you're going to, even if you use different gates, you know that, okay, among these gates, this gate can have much lower latency. So I'm going to assume that, for example, because we want to be conservative in calculating contamination delay. Question? Perfect. Okay, so this is also another recall for you to jog your memory. You know that this sequential system design, we have flip-flops or registers, and then we have some, combinational circuits, and that combinational circuit can also derive another registers or flip-flop. So the thing is that multiple flip-flops are connected with combinational logic, and clock runs with periods, which is TC, cycle time. And this circuit must meet timing requirements for both R1, register 1, and R2 in this example, for example. So we need to ensure correct sequential operation, meaning that, for example, talking about this R2, we need to ensure correct input timing on R2. Specifically, D2, which is the output of this combinational circuit, must be stable at least T setup before the clock age, and at least until T hold after the clock age. So this is the definition for setup time and hold time. You need to make sure that D is stable during this aperture time. So then this means there is both a minimum and maximum delay between two flip-flops. If this combinational logic is too fast, so when we have clock, when you have this rising edge of clock, this register can basically start changing, right? And then Q1 is going to also start changing, meaning that then we have this combinational circuit, and in the end, D2 will also start changing. So if this combinational circuit is too fast, then it might be also the case that for R2, we have this T-hold violation. You can see from this example here that we have this clock, and then Q1 starts changing at this moment, which is the contamination delay. And the moment that you have this change in Q1, this combinational circuit also starts reacting. And then you also have this contamination delay for this combinational circuit. And in the end, your D2 starts changing at this point of time, even though it should actually stay stable until this point, which is T-hold. So you can see that now we have T-hold violation. So that's why our shortest path latencies are also very important, specifically for T-hold violation. And if your basically combinational logic is too slow, then you might have T setup violation. So it takes that amount of time until you have stable output, basically stable data on D2. But this already violates T setup because this D2 should be stable at this amount, at this point of time. in order to make sure that setup time is basically preserved. So now we have potential T setup violation here. So we always need to make sure that we have safe timing, and that safe timing depends on the maximum delay from R1 to R2. The input to R2 must be stable, at least T setup before the clock edge. So let's make some calculation. This is for setup time constraints. So essentially your clock cycle time should be greater than. So you need to make some calculation about the length of this clock cycle. So you have this propagation delay from clock to Q. So that's why we have this T PCQ here. And then you have this propagation delay for your combinational logic. Plus, you need to make sure that your D2 is stable before setup time. So you add it also. Then you need to basically, that's your clock cycle. So your clock cycle should be at least summation of these values. So this gives you some insight here. Whenever you see that your setup time is violated, one easy way to fix is to just decrease your clock frequency or increase your clock period. Of course, this is not desirable because that can reduce the performance of your circuit, but at least it can fix the correctness issue of your circuit. But we're gonna see that for hold time, this is not that easy. So in this, in every clock cycle, you can see that we have wasted work. This is the only useful work that we are doing because you are doing some computation. You're calculating with your combinational circuit. But these two, like propagation delay from clock to Q and also the setup time, they are wasted work that you need to basically wait for that in order to make sure that your flip-flops are working correctly. And this is actually called as sequencing overhead. Amount of time wasted each cycle due to sequencing element timing requirements. And these are sequencing elements, essentially, flip-flops. Any question? Does this equation make sense to you? This T clock should be greater than these values. Okay, good. Usually it's not that easy. I mean, it seems easy when you see it, but you need to think about it actually a bit more and to digest it. But when you get the concept, you're going to see that this is very easy. Okay, so that's the setup time. And essentially for your critical path of your circuit in the combinational circuit would essentially determine your clock cycle. Because in this clock cycle, you can see that this propagation clock to Q is kind of constant. It depends on your flip-flop that you're using. And setup time is also constant. You need to assume some setup time for your flip-flop that you design. But propagation delay of your combinational circuit can be different. And it depends on your, basically, the circuit that you're implementing. So overall design performance is determined by the critical path. And that determines the minimum clock period or maximum operating frequency. If the critical path is too long, the design will run slowly. If critical path is too short, then each cycle will do very little useful work. Remember that combinational circuit is the useful work that we are doing. And all other, like propagation delay of clock to Q and T setup, they are the sequencing overhead that we have. So we need to make sure that basically that sequencing overhead does not dominate, essentially your clock cycle. Okay. Now let's take a look at hold time constraint. So for hold time, we want to make sure that our basically D2 stay stable after the clock cycle, after the rising edge of the clock, at least for T hold. So for that, in order to calculate the minimum latencies, as I said, because we want to be conservative, we go with contamination delay. So essentially, the minimum latency that would cause D2 to change is contamination delay of clock to Q and contamination delay of this combinational circuit. And this should be greater than hold time, essentially. And you can see that this equation has nothing to do with clock cycle. And that's why if you have hold time violation, you cannot fix it by clock cycle. As I said, with setup time, if your setup time is violated, you can just reduce clock frequency. But for hold time, you need to basically, sometimes you need to actually change your circuit. And we're going to see in an example how we can do that. So your contamination delay of your combinational circuit should be greater than T hold time minus contamination delay of your flip-flop clock to Q. Okay, so these are basically summary of these parameters that you can also check later. But now let's go over these numbers with this example. So this is our example circuit. We have 4 flip-flops here and 2 flip-flops here, and then we also have this combinational circuit in between. And these are the latencies that we're going to assume. This is contamination delay for clock to Q, 30 picosecond, propagation delay clock to Q, and so on and so forth. Okay, let's make some calculation. We need to calculate first latency propagation delay of our combinational circuit. Anyone? Any guess? Yes?
So we have that it's 35 picoseconds per gate. At most we have 3 gates. So it's 3 times 25, which is 105.
Exactly. So that's your longest pass. What would your contamination delay? You just go with the shortest pass. So there are 2 actually shortest pass. You have this shortest pass and also these 2 short. And then you also need to get your contamination delay. So for each of them, we know that the contamination delay per gate is 25. Then the contamination delay of this circuit is 25 picoseconds. So now we want to check setup time constraints. So we know that the clock period should be greater than this equation. So we just make this calculation. Propagation delay of clock to Q is 50 plus 105 that we already calculated, and setup time, which is 60. Then you're going to see that, okay, clock period should be greater than 215 picosecond, meaning that your frequency can be at most 4.65 gigahertz. That's your frequency. Now let's check hold time. So for the hold time, the contamination delay of your flip-flop is 30, and the contamination delay of your combination circuit is 25. So 30 plus 25 is 55. And you can see that it's not greater than your hold time, which is 70. And now we have hold time violation. So any idea how can we fix it? Yes? Yes. Essentially, you need to add logic in order to, basically, you need to artificially increase the latency of your circuit. So you add these buffers, and then when these buffers does not change your longest pass, still your longest pass is that. So setup time calculation is not changing at all. But for the whole time, now you have basically contamination delay of 2 gates. So it's going to be 2 times 25, which is 50, plus 30, which is 80. So 80 is greater than 70. So now we don't have hold time violation. Make sense? Okay, let's see. Okay, so I think I'm not going to start clock skew because this we need some time. So let's have break until 3:15, and then we will continue. Okay, let's continue. We still have a lot to cover today. So we already talked about sequential latency and how to ensure we don't violate setup time and hold time. But essentially, to make matters worse, clocks have delay too. Basically, the clock does not reach all parts of the chip at the same time. And that's, we call it as clock skew, time difference between two clock edges. So here is an example. For this flip-flop, for example, your clock reaches at this certain time, but then this is your clock source. It may take a lot of longest paths to reach to the second flip-flop. So definitely, this flip-flop would also would see the clock a bit skewed, which is because of long, slow clock paths. So here also showing this waveform using our abstraction showing of waveforms, that this is your clock source. And point A, because it's very close to clock source, is observing the same, but in point B, we are observing a bit skewed. And that can cause issues. Here is an example from a real processor, alpha processor, that they show the clock skew in the chip. And you can see that in the horizontal axis and vertical axis of your chip, you actually see different skews. So now we need to revisit setup time and hold time while we have clock skews. So the thing is that for setup time, clock can arrive at register 2 before register 1. Meaning that your register 2 would see the rising edge of the clock earlier than register 1. And that's why is it important? It's important because your latency, your setup time now needs to be increased. So I'll show you with this example. So this is your clock 2, and it comes earlier, and this clock 1. And then you can see that Q1 starts to change a bit late, because clock 1 actually comes late. And that's D2 also gets delayed because clock 1 comes late. And as a result, if you don't consider the fact that you have clock 2 is earlier than clock 1, then you may violate setup time. So in order to fix this issue, we need to increase potentially our setup time. And in our equation, we just add a skew to this equation. And we call it as an effective setup time. So essentially, you need to calculate the worst case scenario for your skew. And then you add that to your setup time. And that would be your setup time, essentially. Effective setup time that you need to use it in your calculation. So for hold time, we think not another way around. We think that we consider the clock arrives at R2 after R1. So that can increase the minimum required delay for the combinational circuit. Why is that? Anyone can provide some interpretation. Yes?
The signal starts changing earlier because the rising edge arrives earlier.
Is fast. Yes, exactly. So Q1 and D2, they start changing earlier because we get this rising edge of R1 earlier, essentially. And that can violate hold time for R2. So in order to consider that in your equation, you need to add T skew to your hold time as well. And this is going to be your effective hold time latency in the end. Good? Okay. So yeah, that's a summary that basically you need to that increase your sequencing overhead because you need to add that skew to your setup time and hold time, and then you're going to have less useful work done per cycle. And designers must keep skew to a minimum, which requires intelligent clock network across a chip. And there is actually research a lot going on in this topic that people try to clock, design the clock network in order to make sure that clock arrives at all locations at roughly the same time. There are many, many different ways of doing that. H3, for example, is one of the famous way of clock network, but there are also many other. But that's still a big problem for designers, essentially. Question? I remember that I said that in the previous lecture, we had this example that we wanted to divide the clock frequency by 3, right? And we were using FSM, to divide the clock frequency by 3. And I said that, okay, this is an example, but this is not the way when you want to change the frequency of clock cycles. Because if you get the clock network, actually you have different layers usually in your chips to route clock wires. And when you want to do some computation on your clock, to change your clock, you basically need to bring that clock wire to your logics. And that's caused some delay, actually. That can exacerbate your skew. And that's why people try to not touch clock network at all. So they try to avoid basically doing computation on clock cycles. So the clock can be only used as the input for your flip-flops, but not as input that you want to also operate on clock and make a difference to your clock frequency. There are some analog circuits, like PLL, for example, that they are designed in order to basically change different frequency, provide different frequency of the clock. I'm not sure in the FPGA that you are using in the lab if it is provided or not, but for example, in FPGA also, you can choose the clock frequency that you want your design work. And there is a PLL there that actually by configuring that PLL, you can choose between the clock frequency that you are looking for. Okay, so now let's get to the another interesting part of this lecture, which is circuit verification. And the question that we want to answer here is that how do you know that a circuit works? So we design a circuit. There are several questions that we want to ask. Is it functionally correct? Even if it is logically correct or functionally correct, does the hardware meet all timing constraints? How can you test for functionality timing? And to answer that, we have different ways of that. We actually rely on simulations a lot. So there is a formal verification tools like SAT solvers that they are useful. They can provide like theoretical foundation that this design works, but they're also expensive, and you cannot use them easily for very, very complex and big designs. We also have this HDL timing simulation like Vivado that you're going to use a lot in your labs. And we can also do these simulations at the circuit level, at the transistor level, using tools like SPICE, for example. But in general, testing large digital design is not easy, and it's the most time-consuming design stage there are reports that actually like 70% of the design time in a modern processor actually needs to be allocated for this verification. So a lot of effort needs to be done in order to make sure that that design works correctly. And basically, test engineers, they have to do a lot in the design process of the modern processors, as well as any logic, like memory chips as well. So we need to make sure the functional correctness of all logic paths, timing, power, etc., of all circuit elements. For example, you want to make sure that your circuit is not going to consume power which is not a load. For example, you want to put a circuit in your, for example, ear to use it, and that circuit you need to make sure that your ear does not burn, essentially, right? So that circuit should not, for example, consume more than, I don't know, some microwatt. You need to make sure, right? It's not easy. So you need to test it and make sure that design is not going to consume more than some amount of power. So unfortunately, low-level circuit simulation is much slower than high-level, like HDL and C simulation. And the solution that people devise for that is that they split responsibilities. We usually check only functionality at the high level, C or HDL, which is relatively fast simulation time that allows high code coverage and is much easier to write and run tests. And then we check only timing, power, and etc. at low level, meaning at circuit level, for example. So for that, we don't do any functional testing anymore. And then instead, we try to only make sure that the functional equivalence is correct. So our circuit has this function, like we test the functional equivalence to the high-level model of the circuit that we have. And for that, also, there are some theoretical foundation that people are following, meaning that if your HDL circuit, if HDL code, you follow the principles well, and you write a good code, I mean, your code is synthesizable well, then this gate level synthesized version of that, or even lower than transistor version of that, transistor level version of that would work the same. Like in terms of functionality would be correct. So the functional equivalence would be there. But your circuit level simulation might not might violate timings. And that's another issue which you need to fix. But still, this functional equivalence is also hard, but easier than testing logical functionality at low level, essentially. Any question? Good. So we have tools to handle different levels of verification. We have logic synthesis tools that guarantee equivalence of high-level logic and synthesized circuit level description. That's what I said. So in Vivado, when you input your HDL code, the logic synthesizing tool that you have, and Vivado is not actually the exact great example because the tool chain is for FPGA. But for example, design compiler for Synopsys. When you input your HDL code and your HDL code is synthesizable, then your gate level output is actually has this exact logic that you are looking for. But for timing verification, you need to use some other tools, and these tools check all circuit timings. And there are also design rule checks to ensure that physical circuits are buildable, essentially. So the task of a logic designer is to provide functional tests for logic correctness of the design, for logical correctness of the design, and also provide timing constraints like desired operating frequency. As well as also designer need to be involved also into timing as well. As we already seen, when we have whole time violation, designer actually need to change the design. So unfortunately, designer also needs to deal with timing as well a lot, like how to fix the timing. It's not only saying that, okay, these are my constraints and then make the circuit for me. You also, at some point, the designer also need to find solutions in order to fix the timing violations. There are tools and circuit engineers, and they will decide if it can be built. Like in the end, tools and or circuit engineers will decide if your circuit can be built. But we will first start with functional verification, and we will actually go into a lot of detail in this part because you're going to use this a lot in your labs, essentially. So the goal for functional verification is to check logical correctness of the design. Physical circuit timing, like setup time and hold time, is typically ignored. Like all timings actually usually are completely ignored in this logical correctness test. We may implement simple checks to catch obvious bugs, but basically the goal is to not really make sure that your design is not violating any timing. And we will discuss timing verification later soon in this lecture. There are two primary approaches. One is logic simulation using C, C++, Verilog test routines, or using formal verification techniques like SAT solver, for example. But in our course, we actually use logic simulation. So let me introduce you to Test Bench. So Test Bench is a module created specifically to test a design. Our design that we want to test it, we called it the device under test, which is DUT. So this is your test bench that has different parts. In this part, you need to generate some test pattern, like the patterns of different inputs that you are looking for. And then you input these test patterns to your design under test, device under test, sorry. And then you need to have a logic to check the outputs and see that if everything running correctly or not. So yeah, again, a test bench provides inputs to the DUT, and these inputs can be handcrafted values or can be automatically generated using some sequential or random values. And the test bench has to check outputs of the device under test against handcrafted values again, or a golden design that is known to be bug-free. We're going to see about golden design very soon, but very briefly, you may have a model of your design that you call it golden design, and that usually is implemented with much higher abstraction, and you're sure that that golden design is bug-free. Of course, to make sure that is also bug-free, there is also a lot to do. But as long as you are sure that golden design is bug-free, you can just compare the output of device under test with the output of your golden design. And then you can see that if your design works correctly or not. We're going to see more about that soon. A test bench can be implemented in HDL code written to test other HDL modules, or can be also circuit schematic used to test other circuit design. But we're going to use HDL code in this course. And as you also probably know, and we also discussed a bit yesterday, test bench is not designed for hardware synthesis. So it only runs in simulation only, and there are many commands in your test bench that they are not synthesizable, like definition of these timing, some delays that we're going to use in order to generate some pulse. So all of them are not really, or maybe you have some function like print display. I mean, these are not synthesizable, right? But you are using them in your test bench in order to test your system for simulation. And this test bench can be also in HDL simulator, like Vivado simulator, or can be also in SPICE circuit simulations, for example. But SPICE circuit simulation, we are not covering at all in this course. So don't worry about that. Test bench uses simulation-only constructs, like wait, for example, 10 nanosecond, or we are considering ideal voltage current source. And of course, they are not suitable to be physically built. There are three common ways of Verilog test bench types. One, it would be, we call it simple, which in the end, for input and output generation is manual, and error checking is also manual. So you, as a designer or the one that you are doing tests, you need to do all these tasks manually. We can also do it, have this in a self-checking, like input and output generation is manual, but error checking is automatic. And we can also do everything automatic, meaning that input, output generation, and error checking are all automatic. And we're going to see with some examples very soon. So we're going to use this silly function to walk through these different kinds of test bench, basically the common ways that you can design. So this is definition of your module, and you can see that we are using gate, this completely structural way of programming, and we are using gates, not and or. Of course, this is not the best way, but this is very good way of designing for the sake of our example that we're going to see today. So before jumping through the different basically test bench that we can write for this code, let me introduce you some useful Verilog syntax for test benching. One of them is initial block, which is similar to always block. You can actually also have some sensitivity list for initial, but here, for example, we don't have. And initial actually is, executes only one. So when you enter your initial block, that's the difference between initial and always block. In always block, you always basically try to repeat it, but in initial, you only execute it once. So you can use it in your Verilog. And also this notation like #10 showing the latency, that we wait, or for example, do nothing for 10 nanoseconds. And you can also print stuff in your console in Vivado, for example. You can use this operation $display and basically is string that you're gonna be showed. Okay, now let's start with simple test bench. This is our test bench 1, and we want to test our silly function. So we need to instantiate from our function, as you know. So when you have this test bench, actually your test bench is going to be your top level module. Remember our bottom-up design. So your test bench you can consider as your top level module, and there is a sub module that you are actually instantiating, and that sub module you're going to test it. So your top level module test bench has no input output, but has some values internally has some wires and registers. So you instantiate from your module that you want to test it. And then you, in the initial block, you're gonna basically give some values to these inputs. Like for example, you put A0, B0, and C0, and then wait for 10 nanoseconds, and then change the input C to 1, then wait for 10 nanoseconds, and then another bit vector, another, and another. So once you have this, and you can run your simulation, and then you can generate the waveform diagrams. And in waveform diagrams, you need to manually check basically the output and make sure that output actually is correct for different combination of these inputs. So as you can see that this is not this is easy to create, but it's not really easy to check, and it's not really scalable when your design gets more complicated. So as pros is like easy to design, can easily test a few specific inputs like corner cases, but as cons, like not scalable to many test cases, and outputs must be checked manually outside the simulation, which is not easy. And it's very much similar to printf style debugging. When you want to debug, for example, your Java code, C++, you know, one way is to add a lot of printf, you know, which is not the best way of debugging for sure. Another approach would be self-checking test bench. So yeah, again, you are instantiating from your silly function, and this is your initial block. You are initializing these values, but then you are actually checking the output of these input in your code as well. So you are not checking the output in your waveform. So you know that the output should be 1 for this input combination. So you are saying that if 1 is not equal to 1, then display this input vector 0, 0, 0 failed. So, and with that, you can see basically some errors essentially. So pros are still easy to design and easy to test. Simulator will print whenever an error occurs, but cons is still not scalable to millions of test cases, and easy to make an error in hand-coded values. So you make just as many errors writing a test bench as actual code. So there is no guarantee that you are not making errors while you're writing your test bench, right? Because I mean, you can make errors. Humans make errors. And hard to debug whether an issue is in the test bench or in your device under test. You can also make it a bit smarter, and you can use test vector file. So you can put different, basically you can make a file and then put input vectors and the output that you are looking for in them. Like here is an example. And then, so this actually test vector can be created manually or automatically. Manually is designer just fill it up, or automatically can be also basically created using your golden model. that we're going to also see very soon. So the way that we use this test vector is that you need to read values from your file, essentially. So you have a test vector and it's stored in a file. You need to read it. For that, your book consider that there is a clock. So this clock has nothing to do with the clock that you're gonna add to your circuit for your sequential circuit. This is another clock that you're gonna consider only for your test bench. So in the rising edge of your clock cycle, you read from your file and apply input to your device under test. And in the falling edge of your clock cycle, you check the outputs on basically of your device under check to see if it's working well or not. We're going to see with example. But just make sure that do not confuse this clock cycle with the clock that you are inputting to your sequential circuit. This is different. Okay, so here is a Verilog code for that. So yeah, this circuit, for example, again, our CD function didn't have a clock, but here we define a clock specific for our test bench. And we need to generate the clock cycle for that. This is a very normal way of generating clock cycle in your test bench. You need the always block, and you say that, okay, begin clock 1, and then you wait for 5 nanoseconds, and you make your clock 0, and then you wait for 5 nanoseconds. This means that your clock period is 10 nanoseconds. And this will repeat all the time because your always does not have any sensitivity list, essentially. Okay, and in the initial also statement, you need to read, basically you need to open this file, example.tv, the file that we have all the inputs, vectors, and output, and map that to test vectors. And test vectors is essentially defined here, is as an array of test vectors. It is each element is actually 4 bits in our array. Why is it 4 bit? Because we need essentially 4 bit, right? 3 of them for inputs and 1 bit for output, essentially. So that's why we have 4 bits for each element of this test vector. So you open this file and copy to your test vectors. So these read vectors, and you also reset initial vector norm to 0, meaning that you want to start your test from 0. And the number of errors that you have observed so far is you reset to 0. And then you also reset the system. So, and then you wait, essentially. So that's your initialization. Then we have this always at the positive edge of clock that in the positive edge, you're giving input to your basically device under test. So at the positive edge, you read from test vectors, vector norm, which is initially 0. So you're reading the first element. And then you're mapping that to your inputs as well as y expected. Y expected meaning that the output that I'm expecting. So that's why you're basically moving the output to this y expected. So that is stored in your file, essentially. And then we apply ABC inputs on the rising edge of the clock and get y expected for the checking the output on the falling edge. So this rising and falling edge actually are chosen only by convention. Your book actually uses this, but you can use any part of the clock signal as you wish. So this is not really important. Just the concept is important here. So in the negative edge of clock, if it's not reset, we need to check. So if the output of the circuit in that negative edge is not equal to y expected, then we can display errors. And then we increment our errors. And in the end, if outside of this, also we increment our vector norm in order to test the second element, and we need to go further and further. And at some point, you need to see that you need to have the end of your test vector. So you may fill it up as 4 bits binary XXXX, and you check it. If that's the case, then you say that, okay, test completed with how many number of errors that you see. So this is easy again to design and easy to test. And simulator will print whenever an error occurs, and no need to change hard-coded values for different tests. So you have this test vector file, and you don't need to hard-code it. But as cons, maybe still error prone depending on source of test vectors. So how you generate that test vector essentially. Are you using golden basically logic, golden model of your device? If that's also the case, how you're sure that that golden design is error free? So this is not really easy to check. And also more scalable, but still limited by reading a file. And might have many more combinational paths to test than will fit in the memory. But we also have another way of testing, which in my opinion is the best one, automatic test bench, which we use golden models. Any questions so far? Okay, good. So a golden model represents the ideal circuit behavior and must be developed and might be difficult to write. So this can be done in any language or even in Verilog. For our basically silly example, the golden model would be as easy as this, right? So you had this basically Verilog code with a lot of gates, but you could easily write the code with this assign statement essentially. So that's a high level abstraction. So here it was easy, but for many actually real device designs, actually coming up with the golden model is not that easy actually. And there is a team in the design that they are actually working on making this golden model and make sure that is error free. Okay, so golden model is usually easier to design and understand, and golden model is much easier to verify. We hope for that actually. So the automatic test bench is like that. So you generate test pattern and then you input that to your device under test as well as your golden model. And then you check equality of the outputs of these two models essentially. So the challenge is we need to generate inputs to the design, and this can be sequential values to cover the entire input space, or can be random values or something in between, or many other ways also, different ways. So this is a way of implementing this test bench. So now you have two modules that you need to instantiate. You instantiate from device under test and also your golden model. And you give them the same input vector, ABC and ABC. And then the outputs, you need to check them if they are correct or not, essentially. So if output of device under test is not equal to output of your gold model, then you need to display some error is happening, essentially. So as pros, of course, this output checking is fully automated and could even compare timing using a golden timing model. So people also came up with, designing golden timing model to check timing of your circuit. It's not in the scope of this course, but you can search for it if you're interested. And it's highly scalable to as much simulation time as is feasible. And leads to the reason that scalability is important because we want high coverage in our test. So coverage meaning that how many test vectors, for example, you could input and how much you can basically check the outputs. And in the end, if you have high coverage, then you are kind of confident that your design is working correctly. And also the better separation of roles. So now we can separate designers. Some designer can work on device under test, and some other designer can work on the golden model. Device under test testing engineer can focus on important test cases instead of output checking, for example. And as cons, creating a correct golden model may be very difficult, and coming up with good testing input may be difficult as well. So, however, even with automatic testing, how long would it take to test a 32-bit adder? So in such an adder, 32-bit adder, meaning that we want to add the two numbers and each are 32-bit. So in overall, you have 64 inputs. So you have 2 to the power 64 possible inputs. If you test one input pattern in 1 nanosecond, you can test 10 to the power 9 inputs per second, for example. Meaning that this amount inputs per day and this amount per year, and you still need basically 58.5 years to test all possibilities. So that's clearly show that brute force testing is not feasible for most circuits, and we need to prune the overall testing space. So that's why we can use, for example, formal verification methods to choosing important cases. So you can, benefit from different way of ensuring the correctness and combine them in order to have more intelligent way of verification. And as a conclusion, I would say that verification is a hard problem. And that's why actually, as I said, like 70% of the design time on average is allocated to the testing and verification of the modern processor, for example. Any question? And all these tested devices, they may fail when they come to the market, because you cannot have 100% coverage essentially in your test. Okay, let me also quickly go over timing verification and then we will conclude. Any question? Good. So for timing verification, we have approaches. We can also do it at high-level simulation, and because we can model timing using this notation, #X statement in the device under test, which is actually useful for hierarchical modeling. We can insert delays in flip-flops, basic gates, memories, etc. I also briefly mentioned that in cell libraries that you have, there are delays of different cells. And after synthesizing your circuit, your HDL code, when you synthesize it to gate level or to gates that they are defined in your cell library, then you can do simulation, which is post-synthesis simulation. And in that, you can actually, all these numbers, if you open that Verilog code, you can see that all these values, minimum, typical, and maximum latency of gates, flip-flops, everything is annotated in that Verilog code. In order to make sure that when you are simulating this circuit, you're considering timings of all these circuits. And that can help you to verify basically timing violation or not in your circuit using simulations. So this is usually not as accurate as real circuit timing, of course, because when we are using these numbers, we are basically abstracting the latency. And sometimes we are actually considering worst case numbers, in order to make sure that the latency that I'm considering is for sure my design would work better than that. So you actually consider sometimes the worst case latency when you want to embed that latency in your Verilog code. So that's why in the end, if you have this real circuit timing, that would be best, but you cannot build your essentially your circuit for every timing verification. But there is also a way that you can use a circuit level system simulator like HSPICE, for example, that you can synthesize and then try to simulate SPICE model of your circuit that has the model in transistors, and this SPICE model can basically model all these resistance, capacitors, transistors that you have, and then you can probably get much better understanding of your latencies. But unfortunately there is no one general approach which is very design flow specific. For FPGA, ASIC, etc., technology has special tools for this. For example, Xilinx Vivado, what we are using for the lab, is actually for FPGAs. For ASIC, for example, we have Synopsys or Cadence tools. These are different companies, and that can be used for VLSI designs. So the good news is that tools were tried to meet timing for you. So we just define setup time, hold time. I mean, hold time is actually defined by your cell library, essentially. But setup times, for example, you can define. Setup. You can also define setup time also. But you also define, for example, the frequency that your design you want to work on. And you can also define the clock skew. And basically, these tools, they are doing their best to make sure that they can meet the timing that you're looking for. And in the end, they usually provide a timing report or timing summary. And in this report, you can actually get some understanding of worst case delay paths, like what is the worst case latency that you have from which input to which output. And for example, you can also get maximum operation frequency or any timing errors that were found. But the bad news is that the tool can fail to find the solution. And the desired clock frequency might be too aggressive and can result in setup time violation, for example, on a particularly long pass. Or you might have too much logic on clock pass that can introduce excessive clock skew. As I said, you should avoid having too many logics on your clock pass. And timing issues with asynchronous logic also, they can also cause issues. So the tool will provide, hopefully, helpful errors, and reports will contain paths that fail to meet timing. Like when it's failed, you can actually get query some of these reports, and you're gonna see that, okay, the setup time failed in a path from input A to output Y, for example. And then that gives you a clue to go into your circuit and try to optimize your design in order to make sure, because you can actually help your basically tool in order to finally meet your desired frequency, for example. Okay, and that these reports can give a place from where to start debugging, for example. So now the question is that how can we fix timing errors? So meeting timing constraint, unfortunately, this is often a manual and iterative process. So meeting a strict timing constraint like high performance design can be tedious as well. So we can try synthesis and place and route with different options. So because as I said, these tools, they are doing a lot of heuristic when they want to optimize and meeting your constraints. So sometimes you can just repeat. And that repeat can maybe fix the problem, you know, because when you repeat and then you start with a different random seed, then that heuristic may work a bit differently. And then you might be lucky and then everything would be fine, you know, and then you're going to get what you wanted. And you can also provide us some hints to these devices, to these tools for place and route. That can be actually used in advanced, for example, place and route for FPGAs. There are some people that they go into the place and route file output and they try to edit place and route in order to make sure that, for example, they reduce latencies. So you can try that, but in the end, that may not work. And you can also manually optimize the reported problem paths. So you can simplify complicated logic. You can split up long combinational logic paths. For example, if you have milli machine, you have several milli machines and you're connecting all these milli machines, you have a very, very long combinational circuit, and that can affect your timing. So you may decide, okay, now I'm going to use Moore machine, and that can fix a lot of problems, for example, for you. So a split of long combinational logic paths is one way. It's not only by changing from milli to Moore, you can also add registers in between. So you can actually divide the combinational circuit into two by adding a register in between. And you're gonna see a lot about that when we talk about pipelining in the processor, in the microarchitectural processor. And also recall that fixing hold time violation, we might need to add more logics. But there are some principles that we need to basically follow when we want to meeting timing constraints. So let's go back to the fundamentals. Clock cycle time is determined by the maximum logic delay and maximum logic delay that we can accommodate without violating timing constraints. So there are several good design principles that we should follow. We're going to also look into these design principles later on when we also look into microprocessor design. But here I'm going to also provide them. So critical path design, we want to minimize the maximum logic delay because this can maximize your performance. And your clock frequency is defined by your critical path design, essentially. And you want to have a balanced design. So you want to balance maximum logic delays across different parts of the system, between different pairs of flip-flops. So you might have one, for example, flip-flop, and then a combinational circuit, another flip-flop, combinational circuit, another flip-flop. So your clock frequency is defined by the longest combinational circuit that you have. You might have some combinational circuit that they are quite fast, but your clock frequency cannot determine by them because you have other combinational circuits that are quite slow. So it's very important that you make sure that your design is balanced. For example, all these combinational circuits have the latency around, for example, 200 picoseconds. It's not good that, for example, you have some combinational circuit in between that latency is like, for example, 50, and some combinational circuit that the latency are, for example, 200, 500. So then your design is not balanced. And that's one of the principles that you need to follow in order to have a very good design. And another design principle that we call it, we like to call it bread and butter, is that we optimize for the common case. But we should also make sure that non-common cases do not overwhelm the design. For example, in your, this actually is going to be more detailed and easy to understand when we get to the microprocessor design. But for example, when there are some input vectors or input patterns that you know that these input patterns might happen much more, like very, very likely, and there are some input patterns that they don't appear much, or they may not appear at all. So if you know that information, you can actually try to optimize your system, your design, for the input vectors that they are very likely happen. So that can provide better, overall better performance. So that's why we are saying that we are optimizing for the common case. But we should also make sure that those non-common case, they do not overwhelm the design as well. Okay. So we learned a lot in this lecture. We covered timing in combinational circuit, timing in sequential circuit, and we also look into briefly about verification, how to functionally verify, and timing verification. And that brings us to the end of today's lecture, and also end of digital design part of this course. Next week, we're going to start with computer architecture, and we're going to start with von Neumann and topics that they are quite interesting. Any questions? Then I wish you a nice weekend. See you next week.